All right, so the other day we talked about standard deviation, and I did have you calculate it by hand, and then we used the Excel spreadsheet. The good news is that in these problems moving forward, for the most part, it's going to tell you what the standard deviation is, and then you're just going to use it. So you don't need to calculate the standard deviation. There are times when we do have to, and I will show you how to do that on a graphing calculator or just on a website. So let's talk about this curve in front of us. So a few things. One, this is called a bell curve. We've kind of talked about this before, and you can see that it is normally distributed. Normally just means it's uniform, so it's symmetric. This played a huge part in the election that we just had, and because this deals with percentages. So I'm going to fill this out for you. I'm also going to put it in Google Classroom because you are going to need to reference this very often. The good news is you only have to memorize these 3 numbers, and they're all whole numbers, so they should be easy to memorize. Some symbols we have to talk about. First of all, we talked about the other day, the capital sigma. We're not going to use that here, but we are going to use the lowercase sigma, that like sideways 6. And remember, that just stands for a standard deviation. Okay. Now you have 2 types of means. You could find the mean of a sample, and you can also find the mean of a population. So for example, if we were talking about the election, if I wanted to say, hey, what's the sample average number of people who voted for Biden or Trump? You could take 6 people from each town in New Jersey and you would get your sample average. Or what we did as a country is we looked at the population. So when they were zooming into all of those different counties in each state, those were samples. And then they were giving us the overall state. That was the population of the state. And so it got to a point where once you hit 99% of the votes, that 1% does not matter in statistics. It is not statistically significant. Those 1% of votes that were outstanding could not have been significant enough to have changed the vote. And so that's what we call having a uniform distribution, and it's called the empirical rule. Okay, and what the empirical rule essentially says is that, let's say this was I gave you guys a test. Okay, now hopefully no one's getting a 0 on the test, but in a test situation, your grades might range from a 0 to a 100. So the average might be 50 if it was normally distributed. Half the class, the majority of the class would get 50s. Hopefully that's not the case. Usually when I give a test, right, or when any teacher gives a test, it's going to have a normal distribution, but hopefully no one's getting a 0. So you might have a 50 here and a 100 here, and in between that is going to be a 75. And so that's the average. Okay. So now let's get back to this little graph here. I'm going to erase this so we're going to have a lot of numbers on here. Okay. In the center of your data is the average, but it's not the average for a sample. So remember we said X bar is the average. That's only for a sample. We want the average for the entire population, which is another symbol. It is this little thing right here, which is called mu. And so we're not using that one. We are using the average for the entire population. That's going to go here. Now, the center of the data, where this bell is peaking, this is equal to 68% of the data. It's called the central limit theorem. I'm not going to prove it to you. Just something that's been proven over time. And it says that if you take a survey or if you do an election, that 68% of the data will lie in this little curvy area here, from here to here. Okay? Now it's evenly distributed. So that means that on each half of that would be 34, and 34. But for right now, I'm just going to worry about the 68. Okay. Now the next number is 95. So it means that from here to here, 95% of your data has been collected. Now, 95 minus the 68 we already have in the middle leaves a total of 27%. So from here to here is 95%. Okay? What I'm trying to look for are the exact percentages that are from here to here. And so it's going to be 95 minus 68, which is 27, divided by 2 is 13.5. From here to here is 13.5. And your last little segment here makes up 99% of the data. So once you have 99% of your data, you can say for sure, without any questioning, what is going to inevitably happen. So if this makes up 99% of the data, 99 minus the 95 we already have is 4. And so that means that 2% of your data is here and 2% of your data is located there. Now, where each of these percentages are your standard deviations. Okay, so from the mean, this is 1 standard deviation. This would be 2 standard deviations and 3 standard deviations. Going to the left would be minus a standard deviation, minus 2 standard deviations, minus 3 standard deviations. So 3 standard deviations as far as you're going to go out on these graphs. Your magic numbers here are 68, 95, 99. And hopefully this will all make sense now. Not now, now. So this is essentially what our problems are going to look like. It's going to say you have an average of 45 and a standard deviation of whatever. See, they're already giving you this number. You're not solving for anything. So this just wants to say, what is the distance from the average? Well, if the average is 45 and you're going 1 standard deviation, you would just add 8.3. Three standard deviations from the mean. The mean is 45. You're adding 3 8.3s. So 3 times 8.3 plus 45. 69.9. I'm going to leave these for you to do. Be careful because you're subtracting. And then all we're going to do here is just practice labeling the x-axis. In this one, the average is 95. The standard deviation is 12. So you're going to do 95 plus 12. 107 plus 12. You just keep adding 12 in this one. And why I'm using a calculator, it's 119 plus 12 is at 31. And then you go the other way, 95 minus 12. And so that's how you set up your axis. I'm going to leave these for you to do. And then let's hold off on there for right now.